Hello, and welcome to this presentation outlining my investigations into utilizing Orca and Python to investigate bond lengths, dissociation energies, and orbitals of diatomic molecules, as well as radial functions and radial distribution functions of hydrogenic atoms. For this lab, I was assigned three tasks, which required a variety of visualization software and coding software. The primary coding language I used here was Python in the Jupyter Notebook, using both pre-written code and adapting it to my needs, and writing my own code from scratch. I also used Orca to optimize geometries and calculate various aspects of the molecules I was investigating, such as the Mulliken partitioning and single-point energies. Avogadro is a visualizing software that I used to calculate the bond lengths of several of the investigated molecules and also to see if the bonds were single bonds or double bonds. VMD is a visualizing software that used the output from the Orca calculations to visualize the orbitals around the homonuclear diatomic molecules that were studied. In particular, VMD hoped to show the shape and positive or negative parts of the orbitals. The first task had several parts to it. The first part was to optimize the geometries of hydrogen fluoride, hydrogen chloride, and hydrogen bromide, which meant finding the equilibrium bond distance, the distance at which the bond energy is at a minimum. This was achieved using Orca, with the basis set of STO-3G, or Slater type orbital 3 Gaussian, meaning that the three primitive Gaussian type orbitals were fitted to a single Slater type orbital, and then the geometry optimization was achieved through using Orca's built-in optimization function, opt. Subsequently, the results we achieved were, for hydrogen fluoride, 0.955 angstroms, for hydrogen chloride, 1.313 angstroms, and for hydrogen bromide, 1.412 angstroms, which is as we expected since the bond lengths would get longer with more electron shielding. A larger amount of electrons means less attraction from a nucleus, and so a greater bond length. The second part of the task was using the Orca output files to ascertain the localized charges through Mulliken partitioning. This gives us an insight into the relative charges on each of the atoms in the system. The three Mulliken atomic charges are shown here, and as expected, fluorine is the most negative charge as it has the highest electronegativity, followed by chlorine with the second highest, and finally bromine with the third highest. This follows the trend that would be expected, just as the bond lengths did. The final part of the first task was to put the proposed systems through Orca with differing bond lengths, or radiuses, and obtain the single point energies from each calculation, and plot them in a graph. This is the raw data that was obtained, and from which the graphs were drawn. It was important to obtain the equilibrium bond distance, since before the equilibrium bond distance, the calculations used were restricted Hartree-Fock, and after the equilibrium bond distance, the calculations were unrestricted Hartree-Fock. The difference between these methods is in that restricted Hartree-Fock, the spin orbitals in both atoms are considered to be equivalent, whereas in unrestricted Hartree-Fock, the spin orbitals have to be calculated separately, since the electrons are no longer paired or interacting, which leads to a longer computing time. The only thing to note here are that the equilibrium values from before have been included, and that the energy becomes more negative until the equilibrium bond length is met, and then the energy starts to become less negative, indicating that the equilibrium bond length is the minimum energy configuration. And these are the graphs of the final single point energies plotted against the distance in angstroms. As expected, all of the graphs show a curve, which bottoms out at the equilibrium bond distance, then starts to increase after. The graphs all look similar, but the increase after the equilibrium bond distance is much sharper for hydrogen fluoride than for hydrogen chloride or hydrogen bromide, with a small anomaly around 1.4 angstroms, but this can be attributed to the relatively small dataset that was used. If we had used a larger dataset, the curve would likely have been much smoother. Using these graphs, we can calculate the bond dissociation energy by subtracting the minimum energy from the energy at a point of separation, 3 angstroms for instance. The bond dissociation energies are shown below the graphs. The trend follows as would be expected. Hydrogen fluoride has the highest bond dissociation energy, and hydrogen bromide has the lowest bond dissociation energy. The second task we had was to obtain specific orbitals for diatomic molecules through Orca. The molecules under investigation are diatomic carbon, nitrogen, oxygen, and fluorine, with orbitals obtained and visualized for each, and bond lengths measured for each. To kick things off, diatomic carbon, which was found to have a bond length of 1.223 angstroms. The orbitals are pictured, with the diatomic molecule in the center of the orbitals, and the orbitals assigned to 2s or 2p with their correct designation. It's worth noting here that the positive part of the orbital is in red, where the negative part is in blue. The second molecule to be investigated is diatomic nitrogen. This was found to have a bond distance of 1.134 angstroms. The orbitals have been assigned appropriately. Carbon and nitrogen have the same orbitals, but different bond lengths. Moving on to diatomic oxygen, a bond length was found to be 1.217 angstroms, which is longer than diatomic nitrogen. Also interestingly, where in nitrogen and carbon the sigma G orbital came after the pi U orbitals, in oxygen, as well as fluorine, which is coming next, the sigma G orbitals comes before the pi U orbitals. The reason for this is that the sigma G orbitals are reduced in energy going across the period. Until nitrogen, sigma G is higher in energy than pi U. However, once we reach oxygen, sigma G is lower in energy than pi U. The reason for this is that the sigma G orbitals have more S character and so are more affected by higher nuclear charge. Finally, diatomic fluorine, found to have a bond distance of 1.315 angstroms, which is again longer than diatomic nitrogen and diatomic oxygen. We can see here that just like diatomic oxygen, the sigma G orbital comes before the pi U orbitals, which satisfies what was said about sigma G being lower in energy than pi U. The other part of the task which we were assigned was investigating how changing the charge of diatomic oxygen changes the bond length. Initially, at a neutral charge, diatomic oxygen has the bond length of 1.217 angstroms and a double bond between the two atoms. As we change the charge on oxygen, take 2 electrons out and give it a charge of +2, the bond length is shortened. There is still a double bond between the molecules, but the bond length is now 1.148 angstroms. This is due to less electron-electron repulsion, which allows the bond to pull the two atoms closer together. Finally, when we give the molecule 2 more electrons and give it a charge of -2, the bond length significantly increases to 1.460 angstroms. Since there is more electron shielding, there is more repulsive force, which pushes the atoms further apart. It's also interesting to note that there is only a single bond rather than a double bond, as less electrons need to be shared to complete the valence shell and thus achieve stability. In the third task, the objective was to find the radial function and radial distribution function of the 2s and 2p orbitals, coding it in Python to produce graphs. Firstly, the 2s radial function was plotted. However, for the radial function to have physical meaning, we need to find the square of it. So on the same axis, we have both the radial function of the 2s orbital and the square of the radial function of the 2s orbital. To the right, the radial distribution function, which is the integral of the area of a sphere, the area of the sphere being 4/3 pi r cubed. So the integral of this sphere is 4 pi r squared, multiplied by the square of the radial function. This gives us the probability distribution of finding the electron in certain space, with a maximum around 6 atomic units. It's interesting to note that the radial function crosses the x-axis at a radius of roughly 2, which corresponds to the minimum on the radial distribution function, indicating a radial node, where the electron will not be found in space. Now the radial function of the 2p orbitals. Here, again, we found the radial function and plotted it, then squared it so it has physical meaning. Then we multiplied that by the integral of the area of a sphere to find the radial distribution function. One of the main things to note here, where the 2s orbital crosses the x-axis and subsequently has a radial node in the radial distribution function, the 2p function does not cross the x-axis and so has no radial node. The reason for this is that the number of radial nodes is equal to the orbital number, in this case 2, minus the L quantum number of the orbital. For s orbitals that's 0, where for p orbitals that's 1, and then minus a further 1. So, for the s orbital, 2 minus 0 minus 1 equals 1, which corresponds to the number of radial nodes. For the p orbital, 2 minus 1 minus 1 equals 0, so there are no radial nodes in the 2p. Using the two graphs, we can also ascertain which orbital is most likely to have an electron at a distance below the Borg radius, the p orbital, since it does not have a radial node. The final part of this task is the representation of the 1s orbital in the xy plane, meaning that z equals 0. The z-plane is not considered. Here, both the initial function, the black line, and the square of that function, the red line, are shown. Thank you for watching my presentation.